and believe it or not, he found an old KLM Sky i4 analog receiver dating back to 1984. In fact, this one right here. I think I can safely say that this satellite receiver is part of our satellite heritage. So Tony, how does it work and where does it come from?
This particular receiver once belonged to the American Embassy in Wellington and proudly reproduced the American Armed Forces Radio and Television Service, AFRTS, and in later years WorldNet, or as it's called today, VOA or Voice of America. The Sky i4 receiver was modified by us to work on 240 volts, and it was also modified to work on half transponder frequencies using a 7-meter solid dish that was inside the compound of the embassy, and it was locked onto Intelsat 4, Intelsat 4A, Intelsat 511, and in latter years IS 701 in 1995. The receiver works on a 70 megahertz input. Latter receivers worked on L-band block frequencies of 950 to 1450 megahertz, which we take for granted today. It actually received the 3.7 to 4.2 signals via the feed horn, which is made by Chaparral. It was called the Super Feed and was the industry standard back in 1984-85. And for Intelsat use, we had to put a Teflon slab inserted in the throat here in the waveguide, which whichever way you position this relative to the probe in the LNA gave you the correct polarity. In those days we didn't have linear polarity like the Pan Am sats and the later satellites we have. We only had circular polarization, which was right hand. So that's how the satellite was. That's how the feed horn was actually made.
So Tony, since 1984 we've had 5 Intelsat satellites located at 179 and 180 degrees east.
This actual KLM Sky 4 was operational for at least 3 of those satellites and was retired in early 1990 when the embassy upgraded to an LNB and a Wintersat 8000 receiver.
I, like our viewers, am keen to learn how this antique works.
It works in a very similar manner to modern day receivers, but obviously it was a lot cruder being analog back in 1984. The incoming 3.7 to 4.2 signals were actually one polarity, which was circular, not linear like today's satellites, which use both vertical and horizontal polarization. The Intelsats only used right-hand circular polarization. But later on, the RIMSats actually changed that and used left-hand circular polarization. So the incoming signals from the dish were collected at the dish's focal point by the feed horn and converted into right-hand polarization by inserting a Teflon slab in the throat of the feed horn, like so. The LNA, the low nose amplifier, was bolted onto the feed horn, and the position of the Teflon slab relatively to the probe attached to the LNA provided the correct polarization. As you can see here, you can see the Teflon slab and the little probe in the background, which is part of the LNA feed horn structure. This LNA was a wideband device, and its sole purpose was to amplify the weak C-band signals to a level where it can provide sufficient signal to drive the down converter. Normally an LNA such as this 100 degree Kelvin. Today we have 13 degrees Kelvin. Consisted of an incoming probe cut down to mid-band, approximately 3.950 gigs, which passed the signal onto a preamp, which generated an 8 dB gain, which passed to another amplifier, this time generating a further 12 dB gain, and finally onto 2 final amplifiers, each of 20 dB gain, which provided enough signal to drive the down converter. The first stage actually determines the LNA noise figure using gas feds. You can see them there, which didn't arrive on the scene until the early 1980s. Here you can see the input probe and the low loss Teflon or PTC circuit board, which was required as normal Paxlin circuit boards were too lossy and introduced noise. The amplified 3.7 to 4.2 gigahertz output was by this SMA connector, which was connected to the input of the down converter. The down converter passed 12 to 18 volts via the input-output connector here to the LNA.
So the output of the LNA was still 3.7 to 4.2 gigahertz, is that correct?
Yes, the input of the down converter, the signal was still microwave 3.7 to 4.2. The down converter's job was to down convert the 3.7 to 4.2 gigahertz amplified signal to an intermediate frequency, IF frequency, that the satellite receiver could demodulate. Notice I said demodulate, not decode. There are several types of down converters. This particular model worked on the principle of a single stage of which local oscillator, which is tunable between 3.63 gigs and 4.13 gigs. When this is mixed with the incoming arrow signal from the LNA at between 3.7 to 4.2 gigahertz, resultant intermediate frequency is centered upon 70 megahertz, which is outputted on this F connector here. Don't forget that this FM signal, which is 70 megs, has to be further demodulated by the receiver and inputted to monitor a television. The down converter has a microwave input here. There it is there, and it has a 70 megs FM modulated output here, and 12 volt regulated power supply which powers up both the down converter and the LNA. The third wire here is the tuning voltage, which in this case ranges from 4 volts to 9 volt DC.
So the processing of the 70 megahertz FM signal takes place on the receiver, which provides a tuning voltage which tunes the down converter to a specific transponder number.
Correct. The DC tuning voltage is sent up a cable and is provided to this point here, which applies a tuning voltage to the down converter, which provides the 70 megs IF output at this point.
Right, so then we come to the heart of the system, the receiver. Tony, can you guide us through the various stages and tell us what goes on in each, please?
As can be seen from the sticker, which is the original sticker on here, Peter, it's marked 1984. Its first system test was, it looks like on the 7th of the 2nd, and it was by number 13, whoever that was. The assembly QC was on the 7th of the 8th, and the second system test was the 7th of the 24th, and believe it or not, 8 hours burning time. 8 hours they actually used this machine to make sure it worked. The final test was on the 25th of the 7th by the looks of it, and you know, this is now 27 years old. I would like to see some of our modern day receivers lasting this long, wouldn't you? Yeah. Well, the way this works, Peter, is the 70 megs input from the down converter comes in at this point here and goes through this chain and these amplifiers here, which give it about 30 dB of gain by the time it gets to this point here, which is the band pattern. I'm going to go down. When I finish, in the case of the American DOM sets this unit was designed for, the band pass will be set up to have a bandwidth of 26 megahertz and 30 megahertz for a full 36 megahertz IS signal. In the case of the Intelsats, we used half transponder formats using 18 megahertz. So we actually fitted a half transponder filter, which actually used to sit in here, this part here. And this was tuned to approximately 15 megs but sometimes as low as 12 megahertz, which we did by switching the polarity switch on the front here. Alright. The 70 meg IF signal, when it enters the receiver, is amplified, as I said, by several stages of amplification. At this point, the signal is tapped off just before the diode limiter and fed to the tuning meter, which on this machine is a set of LEDs, which in our case they use to display the signal strength. The signal then passes through FL1, the 70 megs filter, which precisely bandwidth limits the signal from here. From here the signal is amplified to restore the appropriate level before entering the FM discriminator provided by an LM1496 or by an NE564 phase lock loop limiter demodulator. After passing through the half transponder filter or divide by 2 prior to processing by the demodulated chip. After this complex signal has been recovered to a baseband signal, it is passed through another stage of video amplification before it is passed through the de-emphasis filter, which rolls off the high frequency components in the signal which were boosted during transmission to result in a flat video response. The broadcaster adds pre-emphasis and it's used to produce better signal to carrier ratios. The low pass filter is designed to attenuate the audio subcarriers located behind the highest video frequency so it does not interfere with the video information. This video filter is designed to roll off the signals above 4.2 megs, although this can be changed for non-NTSC use. The signal is then passed on to the video detector, the PLL demodulator, which can adjust the video polarity and video level before passing the demodulated signal to a further stage of amplification here, and a video clamp circuit which gates out the 30 Hz waveform added onto the video by the broadcaster. A further video amplification stage and 75 ohm termination A further video amplification stage is made. A further video amplification stage and 75 ohm termination is terminated for the video output signal. A second signal from the discriminator here feeds the baseband video for audio tuning and its output. The audio demodulator is used to separate the audio information from the carrier. The audio tuning is achieved by tuning a potentiometer which will take the audio signals from 6 to 8 megahertz and provide them with an output as well. And that in the crux is how an analog receiver works. Obviously it's got preset points where you can modify the tuning high and low levels, but I think the endearing feature of this machine is the fact that it has a dial drive. There's a dial whipping back and forth, and the little wires you see moving with it here are a little LED that when you got onto the signal, the LED would light, showing you what the transponder was. And that's the KLM Sky i4, which was in its day one of the better machines.